Hello guys, welcome back to my YouTube channel Civology. Today I have brought to you another informative and important topic related to civil engineering, that is what is corrosion and why ordinary steel catches rust or corrosion. Now we are discussing over here is ordinary steel. In my previous video we had discussion about stainless steel which does not corrode or catches rust because we have added a special ingredient, or you can say special element, that is chromium up to 10%, which is resistant against rust or corrosion. But in this video we will discuss why ordinary steel catches rust and what are the effects. As you can see over here in this picture, we will see what are the effects of corrosion when steel gets corrosion or rust. What are its adverse effects on concrete. We will discuss this in upcoming slide. So you are requested, if you are not subscribed to my channel, please subscribe it and don't forget to press the bell icon to get more informative video like this. So let's start today's topic. First of all, what is corrosion? American Standard G15 defines corrosion as the chemical reaction between metal and its environment that produce a deterioration of the material and its properties. Corrosion produces rust that has volume 2 to 4 times as that of the original steel. That is what happens when steel catches rust or corrosion. The volume of the steel increases 2 to 4 times as that of original steel, and corrosion also produces pits or holes in the steel, as a result reducing its strength. Now, what are the effects of corrosion on steel? Steel provides tensile properties to concrete to enable it to resist traffic, wind, and other dead loads. Formation of rust leads to loss of bond between steel and concrete, and structural integrity is affected. Formation of rust also reduces the cross-sectional area of the steel, thus reducing its strength. As we have discussed in the previous slide, that if steel catches rust, its volume increases up to 2 to 4 times of its original size. As a result, it start applying pressure on concrete, which is embodying it or which is around it, and as a result the concrete start cracking and the concrete reduces its strength and its cross-sectional area also starts decreasing. The cross-sectional area of steel also starts reducing. As a result, the strength of the concrete is reduced. Now, how rust is formed? As we know that salts dissolved in water, sodium chloride, forms a versatile, highly corrosive solution of sodium ions, that is Na positive for sodium and chloride is Cl negative. The very mobile chloride ions disperse through concrete pores in solution, and where they come in contact with the reinforcing steel, they attack the passive layer. Steel oxidizes in the presence of air and water to form rust, which has a volume of many times that of the steel consumed. As concrete has a low tensile strength, it will crack. The consequences can be seen on the underside of road bridges and many buildings and structures beside the sea. As we know that there are a lot of moisture and humidity around the sea or near the structures which are near to the water bodies. The underside of the bridge, as you can see over here, it catches rust very rapidly, and near the sea where there is a lot of salts and alkalis in the water, these adverse effects are very visible near the seaside or other water bodies. So corrosion of steel reinforcement occurs by an electrochemical process which involves exchange of electrons similar to that which occurs in a battery. The important part of the mechanism is the separation of negatively charged areas of metal or anodes where the corrosion occurs, and positively charged areas of cathodes where a charge balancing reaction occurs. As you can see over here, within the steel, a part of the steel become an anode and a part of the steel become cathode, and ionic exchanges between these cathode and anode starts in the presence of water or oxygen from the air. At the anode, the iron dissolves and then reacts to form the solid corrosion product, which is called as rust. The rust is formed at the metal oxide interface, forcing previously formed oxide away from the steel and compressing the concrete, causing it to spall. As you can see over here, Fe is for iron, which is in the form of solid, and oxygen from the air or atmosphere, which is in the form of gas. When iron and oxygen from air reacts, it forms Fe2O3 in the form of solid, which is the formula for rust. The formula of rust is 2Fe2O3, which is in the form of solid. As a result of the hydration reactions of the cement, the pore solution of concrete tends to be alkaline, with pH values typically in the range of 12.5 to 13.6. Under such alkaline conditions, reinforcing steel tends to display negligible corrosion rates. Due to the porous nature of the concrete, corrosive species and chemical species supporting corrosion reaction can enter the concrete and lead to the corrosion problems. Corrosion damage to the reinforcing steel results in the build-up of voluminous corrosion products, generating internal stresses and subsequent cracking and spalling of the concrete. As you can see over here, this is the porous concrete. As you know that concrete is have pores in a very small quantity, but though it have some pores, and corrosive species may already be present in the concrete from contaminated mixed ingredients. That is, the water we are using during the mixing of concrete may have the contaminants, or the aggregate we are using may have the high rate of alkalis in it. So these are the corrosive species. Corrosive species may enter into the concrete through these small microscopic cracks, and as a result corroding reinforcing steel built, and as a result there builds a voluminous corrosive products, which results in the cracking and spalling of the concrete cover. As you can see over here, as a result the volume of the steel increases and it start contracting concrete, which is very not strong in tension, and it's ultimately start cracking. Here is the corrosive cycle. In the there are a few stages which I'm going to discuss. At stage 1 there are microscopic cracks. Now it is very it has very low cost if we maintain it, if we the maintenance of the steel. As you can see over here, as we go, as the corrosion increases, and the dollar, or you can see over here, the price of the repair is also increasing. At stage 1 microscopic cracks, as you can see over here, initially the concrete appears to be sound with relatively little microscope cracking and no reddish discoloration from the corrosion product formation. At stage 2 visual corrosion, as you can see over here in this picture, reddish color has formed. Microscopic cracks have appeared and the concrete surface is stained by the reddish corrosion products. At stage 3 spalling and delamination. Spalling of the concrete cover over the reinforcing steel is clearly visible. As you can see over here in this picture, the concrete has started to spall away or deteriorate due to the formation of voluminous corrosion products. At stage 4, that is accelerated decay, as you can see over here, concrete has fallen completely and left the have broken the bond between steel and concrete. At stage 4, severe spalling of the concrete cover over the reinforcing steel is evident, leaving the reinforcing steel bars directly exposed to the atmosphere. That's all for today. I hope you have understand the topic. Why does steel catches rust, and what is the formula of rust, and what are the adverse effects of these attacks of rust and corrosion, and how corrosion is formed. For more videos, you are again requested, please subscribe the channel and press the bell icon to get more videos.